All right, welcome everyone. Thank you so much for your attention at the end of the day. I really appreciate it. I am Kate McCullen Press. I'm a senior project manager at the New York State Energy Research and Development Authority, NYSERDA. I am coming at this topic of autonomous technology from the environmental management perspective. Thinking about applications of technology for monitoring the environment and for mitigating potential impacts to the environment. So kind of the last panel that was in this room segued really nicely into this one. NYSERDA, in our mission to develop 9,000 megawatts of offshore wind energy for the state of New York. We have a mission to do that in an environmentally responsible and cost-effective way. And so NYSERDA has invested more than $15 million in both pre-development and environmental research, including one project that's currently funded for glider surveys through Stony Brook University, Rutgers, and Woods Hole Oceanographic Institution to detect marine mammals and to characterize oceanographic conditions. I also want to note that we host the biennial State of the Science workshop on offshore wind energy, wildlife and fisheries. It's a conference where we are hoping to provide new opportunities to discuss innovations in technology with the scientists, regulators, and developers who are making the decisions in this space. So I think whether you come from this topic from the environmental monitoring perspective like I do, or some of the other areas where autonomous technology has been so important, structural inspection, maintenance, et cetera, there are a lot of common themes that you'll hear across our panel presentations today. There are a lot of challenges in operating in a harsh offshore environment, increasingly further from shore and in deeper and deeper waters. Additionally, the placement of offshore infrastructure in the marine environment adds an additional layer of complexity, which can present another series of challenges, especially where it overlaps with historic wildlife surveys that may need to be modified or augmented once developments are constructed. So traditional methods of survey often involve human and vessel-intensive processes with high costs to operate in such a dynamic environment with conditions that present risks to the humans that are working in them. Autonomous technology can provide opportunities to measure and monitor marine ecosystems in a manner that minimizes competition for ship time, provides long-term continuous data sets and monitoring, reduces operational expenses, and additionally, these solutions can have lower impacts on the environment through things like increased precision and lower fuel usage, and a number of other things that I think our speakers will talk about in a few minutes. Another one of the key advantages to autonomous technology that will come up is the wealth of data that it generates. The advanced sensors that are being used, coupled with artificial intelligence, can provide real-time or near real-time information that is so critical for the processes that we're talking about. So I think as I turn it over to our panelists in a minute, I just want to thank you all for being here and thank them for their presentations. And this panel will focus on 3 projects around developing autonomous technology for offshore wind project development and operations that are being funded through NOWRDC. So we've got 3 presenters. Mary Coyne, a program manager from Anduril Maritime, who will talk about fully autonomous subsea asset inspection by a shore-launched AUV. Then we will go to, I practiced this, Guju So, a song, offshore wind platform leader for GE Research, talking about autonomous vessel-based multi-sensing systems for inspection and monitoring. And then lastly, Brian Hernacki, the Chief Technology Officer for Saildrone, talking about renewable powered uncrewed mobile assets to monitor protected marine mammals. And we are going to use the Slido for questions, so please use that throughout the presentations, and we'll get to them during the panel. You can either scan the QR code with your phone or enter the symposium code, and that'll come up again after the presentations. So thank you, and I will turn it over to Mary.
Okay. I have friends with me. Thank you, friends. So can you hear me okay if I stand right here? Okay, I hate standing behind a podium. I'm used to being able to wander around, so this will have to do. So good afternoon, everyone. My name's Mary Coyne. I'm the manager for commercial programs for Anduril Maritime. So what is Anduril? You've probably seen it in the news as a defense company because, spoiler alert, it is. It's primarily focused on DoD contracting. You're talking to the 1% of the company that doesn't do any of that. So what we are focusing on is how do we come up with software and hardware solutions for the offshore wind space, the renewable energy space, and just more generally, subsea surveying overall. I'll get into the details there in a little bit, but it's a pretty impressive company. We're based, our small group, Maritime, it's about 100 people. We're based in Quincy, Massachusetts, so not far, but the footprint of Anduril writ large has locations all over the country. So for the most part, the work that we are conducting is in the Northeast, but we wholeheartedly expect to be branching out into California and deeper waters where we think we truly can shine. So a little bit of background on me, and then we'll dive into what the actual platform I'm talking about is, what the program we're actually running with NowRDC is, and how it's going. So my background, I am not an engineer. I was a submarine officer, so I was an engineer by practice and just relied on in-depth knowledge of other people, but I'm unduly familiar with the hazards of work at sea, especially if you're underwater. And then I moved into GE's renewable energy business, so working in onshore wind for a few years, and then more recently in offshore wind. And one of the more glaring takeaways from that is the amount of work and the amount of surveying that needs to be done for these projects. And does the industry have the scale and the capacity to meet those all on time and safely? And that's largely the question that this organization is trying to address. And I think there's a number of people in this room that are trying to answer that same question. So without further ado, again, I'll give a brief overview on the hardware itself, and I apologize if I squint. The light is right in my face. And then we'll move into the project overall. So just, if you ever want to get a hold of me, here's our information. You probably can find it through the symposium, but I do have some of my colleagues here tonight. We actually have one of our operational hulls with us. So at the reception at the end of the day, we have hull number 6. So she's on her cart, ready to rock and roll with a fresh coat of paint and some gloss. Thank you, Cammie, and thank you, Jess. So if you ever have more technical questions and want to dig into the little details, there's lots of knowledge that'll be present. So what is the Dive LD? The Dive LD is, for lack of a better word, a submarine robot. Rated to about 6,000 meters. She is fully autonomous and untethered. So it's a reliable operation. We can rapidly integrate different payloads. So that means that we can take either commercially available off-the-shelf sensors, integrate it into not only the hardware itself, but our software control systems. And we can also do that with bespoke design and partnership with other clients, such as the Department of Defense and others. So it is quite malleable. There's a lot of different mission sets that she can address. But for the purposes of today's conversation, we are going to be focusing on the commercial applications, i.e. subsea surveying, so cable inspections, foundation inspections, and just generally assessment for obstacles on the seafloor that could interfere with offshore wind construction. So that's the small market we are targeting right now, but I think it's designed to be a bit of a Swiss Army knife, and you can see why. So we've stuffed a lot of sensors into this thing. So we have a sub-bottom profiler, we have a side scan sonar, we have a magnetometer, we even have a camera. Well, it turns out it's really difficult to take high quality pictures in the Rhode Island Sound. It's rather murky, but we're excited to see how this can apply in deeper, clearer, less turbid waters. So the cool thing about this is, as I said before, it's kind of a Swiss Army knife. And what we're working on is figuring out what combination of sensors is the most effective in terms of energy usage, right? So this is battery powered. We have 6 batteries on board. The more sensors you operate at a given time, the faster that battery is depleted, and the shorter your mission is actually going to be. So the more frequently it'll have to come back to shore, either swap out with another LD or charge and then go back out again. So it's that fine balance to figure out what the mission is, what sensors are most pragmatic in executing that mission, and what's the most time-effective course so that we minimize the number of times we have to bring her back for recharging purposes. So this is it in a nutshell. And here's more generally what they do, right? So we have a multi-beam ectosounder. I didn't mention that before. It is in fact on there. Eric's glaring at me. It's a very important piece of equipment. But what this essentially does, and I won't get into each one of them individually, it's a different layer of understanding the different facets of I'm sorry, guys. I'll stay closer to the microphone. It's the different layers of understanding the world below the ocean surface. So not only the topography, but what's underneath the surface. What is the composite material present? So how do we find big boulders that might get in the way of a subsea cable, for example, or artifacts that need to be cleared for, archaeological purposes? These are all very real problems. And so our thought process was, well, let's incorporate the tools as we can. We are not designing any of these sensors. We are integrating what is readily available. And I think many other platforms actively use today. But how do we consolidate them and make it usable with our software? So, moving on. There's lots of things on the Dive LD. I'm excited to show you guys in person tonight what it actually looks like. But what problem are we actually trying to address? So I'm just curious. I wasn't here for the previous presentations, but show of hands, who has actually been out to sea, like the ocean, and had to sleep overnight on a vessel? Okay. Oh, that is awesome. Okay, so a large number of people. So I don't need to reiterate to you how truly awful that can be, right? So it is high risk, especially if you are conducting work that is sensitive to sea state and wind speeds. It is also high risk for the environment. So not only the people doing this work, but the environment around you, as the previous panel addressed in depth. And it's also really expensive. It's really, really expensive. So in light of the fact that there are so many of these subsea surveys that need to happen for this offshore wind work to get constructed safely and responsibly, we wanted to explore how we could use this robot to autonomously leave the pier, conduct a survey, identify anomalies, re-inspect them just to make perfectly sure they're actually the anomalies we want them to be, and then return home and report back on its findings. So how do we essentially take the operator entirely out of the loop? That's what we're trying to prove in partnership with NowRDC and our partner Metron. So what we're focusing on is the subsea cable for Block Island. So we've been spending an inordinate amount of time bobbing around the Block Island Sound. And what we're doing is we are developing our autonomous navigation command and control to be able to not only conduct the survey itself, so go from point A to point B, but also flag errors and flaws in the data it receives, so it has to be trained. We have to build up a library of what is normal and what is abnormal with confidence, and then as a result of that, further instruct itself to revisit those sites. So that's what we're doing. And here it is in picture form. So our general concept of operations for this project is to launch from Quonset, Rhode Island, transit out to the top of the subsea cable, conduct a side scan survey, which is a corridor search, so you basically follow the track of the survey. You don't have to move over it in a lawnmower pattern. And then as it's conducting that survey, this block down here in the bottom corner, this is an image with side scan, for example. Our algorithm can detect errors, so these are just lobster pots, and say, okay, this is where I am, this is what is around me, this I understand, this is how confident I am in that understanding. And oh, by the way, I'm not sure about this flag. And then once that first corridor survey is done, accumulate all of those question marks that it has, create a new path to re-inspect those things, and then come back. So it's a lot. This is very, very, very software intensive. I don't want to hand wave over that because a ton of work has gone into not only developing the algorithm itself and how the machine is controlled, but also the quality of the data we receive and just making sure that our system is set up the right way. So refining how our sensors work. So I do want to call that out because it is hard to put in under 10 slides the amount of work that went into this. But please understand that this is a simplification of a lot of work that has been done. So where are we at? We actually have our final demonstration in March. Hoo-yah. So naturally, we line this up perfectly with winter in New England, so what could go wrong? But just recently, we passed our final go, no-go point with Nauer DC. So it was the development and verification of the autonomy navigation command and control software that meshes with the side scan sonar output and is what enables the robot to identify those flaws, direct a re-inspect mission, and then come back. So this is actually very, very, very labor intensive. This was one of the more challenging hurdles that we had to get over as a business, was proving that software capability. So it's one thing to have the hardware, the robot itself, mechanically and electronically connect all of the systems and make sure they're set up correctly. But ensuring that the robot actually does what you want it to do and follow the behavior trees that you want it to follow logically and predictably, that does take a lot of work. So the good news is we've been able to prove that and verify that. And the next step in January is going to be actually launching the DiveLD robot from the pier in Rhode Island and letting her go off and do her own thing without any operator intervention. So naturally, that's happening in January. We will still be following her from afar. This is one of the first times we'll be doing that with geophysical surveys. So this is a big step for us as a business, but we're looking forward to seeing how that moves along. The last thing I wanted to highlight is just some of what you actually see at the conclusion of these surveys. So I showed you that picture that had the lobster pots and a certain percentage confidence in that, yes, that is a box that has lobsters in it from the robot. But this is what happens when you run multiple surveys using different sensors in a similar location. You can build a more detailed picture. So this is a side scan output overlaid with a magnetometer output of a cable crossing off of Point Judith in Rhode Island in the water. And you can see just how compelling and detailed the final image is if you actually partner two different sensors together. So this is what, in parallel, not only on the autonomy side and actually going to do the surveys, but what the data output is. How usable is it? Is it something that we need to chew on for 3 extra months just to get something our clients can actually understand? Or can we process it intelligently, overlay it with other information we've been able to collect at the same time to make it that much faster for people to understand any flaws or concerning elements of the seabed? So I thought it was a really compelling image. So that's all I have right now. So mahalo for your time, and be taking your questions shortly. Thanks. And then I think Brian, you're up next. Maybe? Oh, no, we do. Sorry, false alarm, Brian.
Okay, good afternoon, everyone. My name is Guiju Song. Mary just talked about the autonomous robot for underwater asset inspection. On behalf of our outstanding team from GE Research, I will talk about autonomous vessel-based inspection for assets above the water. So in next 10-15 minutes, I will firstly talk about some facts and vision for the offshore wind OM. After that, I will talk about our project overview, some technology highlights, and our results. Lastly, I will share some of the future works. From different social media or from your own sources, you may hear about these days some of the pipeline projects have been canceled. People are seeking for renegotiation for the offshore wind projects, and also the cost for the material, for supply chain, everything seems is shaking the confidence of the offshore wind. But the United States government has reiterated the importance of offshore wind. So as a researcher, we are thinking about what can we do, how we can help from the OM perspective to reduce the OM cost and help to regain the confidence and the optimism of the offshore wind. So our vision is really to leverage intelligent automation to reduce the OM cost and reduce the potential risks for doing and maintaining those offshore wind assets. I connected some of the pictures just to give you visually about the environment for offshore wind OM. So you can see from those pictures, there's various of operations, there's various of tasks that involves human to perform these tasks in a very harsh, dirty, and dangerous environment. So to do this, how can we help reduce the risk, reduce the cost? Our vision is really about leveraging the automation, innovation to change the OM paradigm. There are 3 initiatives we want to propose. Actually, Kate mentioned in your opening remarks from data perspective, from AI modeling perspective, from the robots or automation perspective. We use a different terminology. So the first initiative is about Sentinel. Sentinel is a way to place optimal sensors, optimal inspection solutions to help us see the history, the present, and the future of your assets, their health condition, their abnormal condition, and predict what will happen in the future. So the Sentinel is very important, first step. The second step is about, we call it the digital twin. It's about using AI, machine learning, advanced analytics to understand, make sense of the data. So we understand the condition of your particular assets and be able to predict what will happen in the future. The third piece is a caretaker. It's about how can we utilize tools, automation to firstly amplify our humans' capability so our technician can do things more efficiently. Secondly, we can assist the human to take care of some of the tasks we cannot do it today. The third is a little bit long term. It's really about the automation. So we will utilize the automation solution to replace the human to perform this dangerous task. So our people, our technicians can do much more efficient, high-value work in a safe environment. So let me talk about our project funded by now RDC. This is a 12-month proof of concept project. The objective is to develop a long-term resident autonomous inspection robot. These robots can live in a wind farm permanently for long duration commission. And given the high payload, we can integrate all kinds of sensors, inspection modalities on this vessel, so we can perform visual inspection. We can capture 3D profile, just like you guys did. We also can capture defects using thermal, IR, other modalities. So this solution, as I mentioned, can live in the wind farm and perform periodic inspection. Comparing to today's, every 6 months, every 1 year inspection, this can provide us much dense inspection data. With the much dense inspection data, we will be able to utilize the AI power to help us to do the prediction. So you may ask me, hey, drone inspection is everywhere today. It's commercial available. Why are we proposing this new solution? Here's my answer. Comparing to the rope-based inspection, basically it's out of the picture, but some places they are still applying rope-based inspection. Comparing to rope inspection and drone inspection, I already mentioned we can provide a cost-efficient way to give you more inspection data. That's one. Secondly, because this high payload vessel, and we can include multi-modality to provide a different information which is not available, which is not possible today from the drone inspection. So this project has been completed in October 30th after we did a field test in Block Island as well. So besides our outstanding team from GE Research, we also had an advisory committee from GE Offshore Wind, including the product line manager, including our general manager from the sales perspective, and also like a person, also from the OM team like Mike Hansen, who's in charge of this daily operation for the Block Island wind farm and in the future other wind farms in the US as well. So besides the GE team, we have X-Ocean as the vendor who provides the autonomous vessel for us. Just keep in mind that this project is not about innovate or develop a vessel. It's really about developing new sensors. This new sensor suite can be plug and play with any vessel so we can perform inspection for the offshore wind turbines. So let me talk about our technology differentiation and our results. This conceptual design very well explained what we are doing and why we are doing this. So imagine you want to mount an inspection system on a vessel and doing this wind turbine inspection far away because you need to avoid any of the condition to your turbine. Let's say we have a standoff distance from anywhere between 75 meters to 150 meters from the wind turbine. So how can you address the first challenge? You have sufficient image quality, be able to detect 1 millimeter crack on your blade. So that's the number one challenge we want to address. Secondly, because the inspection system is on a boat, you guys know the ocean state, there's always a kind of a multiple degree of motion, right? So when you aim at your blades, maybe due to the motion, your blade will suddenly jump out of your picture. So how can we address this challenge? And then another very important challenge is inspection while turbines are operating. I mentioned the rope inspection, I mentioned the drone inspection. Both of these methods need to stop the turbine. So every 1 minute of the stop means you are losing your productivity. So that's the LCOE impact. Our solution will aim to inspect while the turbines are spinning. So that's the two challenges we are addressing, utilizing our proprietary two-camera system. The first camera on the top, we call it the positioning camera. This positioning camera has a large field of view. This camera can always capture the entire sweeping areas. So we have an AI algorithm to analyze this large field of view images and track each of the blades and some of the features, for example, the nacelle. So once we lose the blades or the wind turbine, this information will be fed to a gimbal system or PTZ system to kind of, pull back the entire system into your line of sight. So that's the first camera called the position camera. The second camera called the tracking camera, its function is about inspecting. So the specific design for this tracking camera allows us to capture high resolution image from that far away and still be able to detect crack or leading edge erosion at a 1 millimeter level. To address these two respective challenges, we built two prototypes. The first prototype is a lab prototype. So from this picture, you can see there's a two-camera system, exactly the manifest as what I just mentioned. Then there's a yellow robot arm. The robot arm kind of mimic the motion from the sea. So there's a 6 degree of motion from the sea. When the robot arm moves, and you can see, sorry, this is a PDF version, I cannot play the video. But on the right side, so you could see, and then the blade jump out of your field of view. But our algorithm will real time provide insight and then guide back the whole position of the system, and then you can track the blade again. So we don't bring the vessel with us in the Navy, what's it called? Navy Yard lab. New lab, yeah, sorry, I'm sorry. But we have the imaging system with us tonight. So if you go to the reception, you will see our imaging system, and in there I have my own computer, so I will play this video for you. So this is a second prototype. The second prototype is to address the imaging quality issue. So we had a design with a very long lens and careful design, choose the camera, the two-camera system that allow us to meet the image quality requirements. This system, as I said, is a plug and play. So we had some fixture design. It's easy to mount the prototype on top of this vessel provided by X-Ocean. And then with that, we were ready to do the field test. Before we went to the ocean test, we also did a factory acceptance test at the Mystic River in Boston. The river environment gave us a water environment, but with much moderate, quiet states. So again, there's two videos showing how the vessel sails to the inspection site, and then how our system over here kind of pan tilt, move around to capture the image. I can play the video in the evening. This is the field testing. We launched the boat from the Port Judith, the same as what they did, and then the vessel sailed to the wind farm. Over there, we inspected 2 of the 5 wind turbines at the Block Island. We got a bunch of pretty images. Of course, the images quantity is good, but with some of the defects from the blade, from the towers. So again, video will be played in the evening. So as I mentioned, this project has been completed in October of this year. I would say we kind of approved the concept of the two-camera design, which provided us reasonable image quality for defect detection, which provided us the feasibility of using another positioning camera to help us do inspection while turbines are spinning. So this is very important from a value proposition perspective. As I showed to you, the first prototype was developed and demonstrated in the lab scale. The turbine is a very small one, kind of a toy scale. So in the future, as next, we will scale this blade tracking lab prototype to a full scale. Potentially, if we aim to 12 megawatts wind turbine GS100X in the future. So that's like a huge amount of scale-up efforts we need to work on, and then integrate again with the imaging system together to perform a pilot test in a real environment. So, thank you very much.
All right. My name is Brian Hernacki. I am the Chief Technology Officer for a company called Saildrone that is based in Alameda, California. It's out near the San Francisco Bay Area, and we build uncrewed sea vehicles. And technically, we build a data as a service platform where we operate the drones to provide data to our customers to solve a variety of problems in bathymetric mapping, marine domain awareness, scientific monitoring, and in the future, offshore wind construction. And before I get into the details, I want to thank Kate because she practically gave our product pitch in her intro. So you saved me a lot of time about talking about all the reasons that we want autonomous sea vehicles, and that the sea is a very difficult place to work, a very dangerous place to work, an enormous place to work that requires a crazy amount of human hours and time and dollars to cover just a tiny fraction of. And we firmly believe that you don't solve problems of these scales without something like autonomous vehicles and autonomous sensing. So I won't read this to you, but we really do believe there's a lot of work exploring, mapping, quantifying, and monitoring the ocean to help solve a wide variety of problems. And that's what we've been at work at Saildrone for over 10 years. We have our fleet of sea vehicles, our fleet of drones deployed around the world today, from the Arctic to the Middle East to South America to the East Coast here, off the West Coast. We make 3 different classes of sea vehicles. The smallest of one is called an Explorer. When I say small, it's 20 feet long. You can actually come see one tonight in the new lab building. I just got a picture of, they got it reassembled inside. It's a little hard to get this massive sail vehicle through the door. The mid-class, called Voyager, which is about 33 feet long. And our largest drone, called the Surveyor, the original was 72 feet long, and the next gen will be about 65 feet long. These are designed to go out into harsh ocean environments, thousands of nautical miles, for months at a time, completely autonomously. They carry a huge variety of payloads. They are solar and wind powered. The smallest one is pure solar and wind. The larger ones have some backup generator for low light conditions. They carry a wide variety of very flexible payloads. The largest one can carry, if any of you are bathymetric nerds, it can carry a Kongsberg 304, which is a huge bathymetric sensor. It can reach down to 11,000 meters. We have a variety of sensors we can put in the keel, on the hull, up on the mast, from PTZ type cameras to radars to scientific sensors, ocean salinity, water column data. They are designed to be a flexible platform to solve a wide variety of use cases. We're going to talk a little bit about what we're doing with Now RDC in a few minutes on offshore wind and marine mammal mitigation, but just to give you a background of what we've been doing at Saildrone. Again, Kate made half this case for me, but there's a lot of challenge to working in the ocean environment, and certainly the risk to crew and vessel operating in this environment is a big one. Safety issues, persistence and duration. Even just from a pure cost perspective is difficult. Remember that 70% of the planet is ocean. And to get sensing over even a tiny part of that, there are not enough ships out there to even scratch that surface. At Saildrone, we focused heavily on the environmental impact of what we're doing. Actually, I have a really neat slide that shows this. Our Surveyor V1 performed a mission about a year ago where it did a 12,000 nautical mile round trip and did over 16,000 square kilometers of seabed mapping with its sonar system. That's primarily bathymetry work. It emitted just 2.7% of the CO2 of a traditional ship to do the same mission. So when you have something that is solar powered and wind driven, it is cost efficient, environmentally low impact. When we talk about marine mammal mitigation and sonar passive acoustic sensing, being quiet is actually a great additive value to the solution versus something out there with big churning motors. As I said, we've been around for 10 years. A lot of this was learning how to operate in marine environments. And you'll see a lot of solutions out there that people have that are electrically driven drone craft in the sky or something like that, where they have durations and ranges that are measured in hours, days, not even weeks, not even hundreds of nautical miles, but they're relatively limited range. It took a lot of learning to figure out how do you trust and send autonomous vehicles out for months at a time and thousands of nautical miles and have them be robust in a very difficult, acidic, thermal environment, high shock environment. The newer classes of drones, the mid and the larger ones, now are equipped with Starlink. We can get an enormous amount of data. We can keep up with most of the bathymetry surveys real time with capability like that. The power systems took a lot of evolution to get them where they are durable for those mission ranges, a lot of custom work in battery generation and power management, and figuring out how we effectively integrate a lot of these third-party capabilities, these sensors. And so whether it is ocean science sensors, domain awareness sensors, cameras and radars and the like, or in the future things like LiDAR for wind farm management. But now we've got a platform that is reliable, and we can kind of turn the crank on that. We can start to apply it to different use cases. One of the projects we've been working on, the one with Now RDC right now, is creation of this new acoustic sensor. The market doesn't really provide one of these today. There are super large arrays out there for things that people do, and there are fixed buoys that people do for acoustic sensing. But what we wanted to do was apply the sort of the drone platform we have and its mobility and its endurance to sensing things like marine mammals. And so we have been constructing this, it's about a 3-4 meter long sensor with like a tetrahedral array and very carefully chosen sensors and frequencies designed for detecting a variety of marine mammal species and the vehicles around them. And the concept is we can take this drone platform that can be out there 24/7, and unlike a buoy, which can be there 24/7, it can move around and cover a very large area. The array itself is designed not just to do omnidirectional, but beamforming as well, which means that you can figure out where the signal is coming from. And if you have multiple drones, they can actually collaborate and not just precisely figure out where that signal is coming from, but track it over time. And so things like aerial solutions where you might catch a whale breach or a plume periodically are going to give you, if you're lucky, a tiny sample set of where those animals are. Whereas if you're doing subsea sensing, things like acoustic sensing, you can much more precisely track those. When you combine that with ability for drones, fleets of drones to do bathymetric survey around a survey site where you're going to build a wind farm, management and upkeep survey where you're trying to track conditions of your substructures, of your cables, and monitoring the site so that you know when you have to perform shutdowns, either during construction or during operation. We think solutions like this are going to be really ideal for that. We have been testing this in conjunction with Now RDC and our partner RPS. We've done a test on the West Coast against the Mbari array near Monterey. We just completed one against the Cornell array up near Cape Cod here. And we're doing another one right now, and I'll show you some details in a sec, down near Cape Fear off South Carolina. These have been on our Explorer class drones. That's the one you'll see this evening. They're small, they're quiet, they're pure sail driven. The Voyager class drones that we will use next year are slightly bigger. They can carry the Starlink system. They can carry a heavier set of ocean science sensors. Your capability to carry sensors is a little proportional to your size. Bigger drone, more solar panels, more power. You can push yourself around a little more, you can power more sensors. And so, of course, our large surveyor can carry even more sensing equipment. We probably think for things like wind farms that are more coastal, littoral range, things like Voyagers are probably a better fit. Surveyors designed to go very deep out into the ocean. You don't really get 11,000 meter surveys too close to the coast in wind farms. I'm not a wind farm expert. I don't know if the floating wind farms are going to go out that far, but I imagine transmission's a factor. This is our first test mission that we did with Now RDC. I mentioned it was near Cape Cod. It was about 15 days. We were trying to collect initial marine mammal data in a very structured way where we could compare ourselves to the Cornell buoys. And then we work with a partner called RPS who does the technical data evaluation. We collected over 700 hours of data. Initial 700 hours of data, a lot to analyze, so they're still working on the analysis of it. It's back any day, any week now in December. The initial, we did a couple sample slices where we knew from the buoys that there were hits. We were able to see North Atlantic right whales. It's a really concerning population that we're trying to manage right now in the larger community. Humpback whales, even dolphins. We think maybe a blue whale, pending the analysis on that. But it was really exciting to see how in this array we've been developing, clear the signal came out, how much we were able to differentiate from background noise and signal noise, in part helped by the fact that we have a very quiet drone. It's very quiet electromechanically. You get some amount of hull slapping and the like, but you don't have a motor to listen to. The vessel itself is very small. It's got a very small amount of draft. It is really quiet, which makes things a lot easier if you're trying to listen. We're doing demonstration 2 right now, again with Now RDC and RPS. Another 2 Explorers, same slightly upgraded acoustic array, another 14 days, running off the coast of Carolina there, again comparing to some set points we have There's a particular area that we want to measure that we believe the mammals are in at this time of year. We're racing a little against the winter. Solar, is starting to get a challenge. Fortunately, we're not at very high latitude or very low latitude. Solar works great when you're at mid-latitudes. If you get up into the Arctic, it gets a little more challenging. That's why our larger classes of drones have the backup power supplies. One slightly exciting thing about our drones, it gets into some of the sessions today have been talking about the need to make this a practical business. We worked with ABS to do the first uncrewed sea vehicle classification. So we got certified as an ABS certified vehicle, which when you get into the business economics and needing to have regulatory surety, manage things like insurance, it might not sound as exciting as the passive acoustic sensing, but it's a fundamental thing to help make a business out of this. And that's, we're a commercial provider. We're focused on helping our partners, our customers, utilize our platform technology to make their business efficient, to collect the data they need, to do it in a scalable way. So doing things like ABS certification is definitely part of that. That's the end of the prepared remarks. I'm excited to get to the panel and hear what you all want to know about. Thank you very much.
So I'd like to invite our panelists to come sit at the front, and please, if you have questions, either scan the QR code to get to the Slido app or put your questions in with a symposium code, and we'd be happy to take questions. But also, all of our panelists will be at the reception later this evening, and you can continue to engage with them.
That's your mic.
I'll share it with you.
You can pass it around too.
Okay, maybe to get us started off, we talked a lot about the benefits of autonomous technology in all of the presentations. Can you all talk a little bit about some of the barriers to development or to adoption that you have dealt with, and kind of some of the potential things that may help overcome those limitations?
Sure. First of all, it's hard. The ocean is a hard place. As I said, it's enormous. It's very corrosive. The thermal environment, the shock environment are hard. And when you put something thousands of miles away, it's hard to go fix it. So this is hard technology development. It takes a lot of effort, time, and resources. But that's on us. That's what we're trying to solve. I think to the community here today, we stand on tall shoulders, and we rely on great science. We're engineers. We're building a thing and making it work, and we rely heavily on the science that a lot of people do. So when we do things like frequency analysis for detection of marine mammals, we are learning and working with the people, learning from and working with the people who have been doing all the science on that. And I think the science research community also provides the impetus to business and the impetus to regulation to drive the kinds of things that we need in something like marine mammal mitigation. There are parts of the commercial sector that are already commercial and healthy, and how people do bathymetric surveys of undersea cables. But when it comes to something like offshore wind and marine mammal mitigation, it's still new, and it requires that science to drive the technology and the science to drive policy. And I think those are also very hard, but we need a lot of help there too.
Now it is. Okay. I actually think, Brian, you teed me up for this with your last slide. One of my first answers is really boring. It's the admin. It's the fact that I think our regulations, so Colregs just working with the U.S. Coast Guard and making AUV work scalable and a sound business choice that is de-risked. And a lot of that comes down to insurance as well. So how are we classifying these assets when they're out at sea on their own? The extra layer that we experience is we are not a surfaced vessel. Most of the time, we are underwater. And the way it worked when I was on submarines was if you're underwater, the rules of the road are a little different, as in you have 3 dimensions that you can operate in. You just stay out of the way and don't hit anything. So what is a safe and reliable and repeatable way that we can apply those classifications to our robot? And that's just one layer of it. So getting some clarity in how We classify autonomous vessels, the rules of how they operate in the larger marine environment, and just so we can shape how we control it and its software brain in a safe way. And then it's from that point, people learn how to trust it. Right now, if I went to a developer and said, we have this autonomous solution for you that will remove human risk, will get the job done, and it's better for the environment, your carbon footprint is lower. That sounds great, but you need to have proof of concept, prove that it's reliable, and people tend to trust things when there are rules applied to them. So it is another chicken or the egg situation here, but to answer your question, Kate, it's admin and classification and overall understanding and trust of the business as it kind of comes to fruition.
So from the autonomous vessel-based inspection for above water assets, just from this perspective, we are seeing two potential barriers. The first one is it's kind of a coexistence question. Because when we went to the Block Island to do the test, it's September 2nd, it's a Labor Day weekend. There's so many fishing, other recreational boats. Everyone was so surprised, hey, what was that? So they got very close to look at the vessel. So this type of coexistence will be a potential issue or barrier. We need to figure out that before the acceptance of using this type of solution. That's number one. Number two is about the cost of inspection itself. So I mentioned the competitive solution is the drone, right? So of course, I don't know what's the profit margin for the drone company. Let's say they only charge you $300, $500 for one turbine. Now we are proposing this autonomous vessel-based solution. The autonomous vessel is not commercially available yet. So there easily talk about 1 million or maybe to 10 million that type of cost for the vessel itself without adding on the imaging system itself and also other services yet. So when we go to the wind farm owner or the OM managers, they will easily ask a question, what's your competitive advantage? Of course, from a safety perspective, yes, we got it. But how about cost? Because I only need $300, $500 for one turbine using drone. So I think that's another barrier we will face when we try to scale up the broader deployment of such a solution.
Thanks. That's great. And I had never thought of public curiosity as one of the things that we might have to deal with. So it was a good point.
It's funny how many people take pictures of our drones.
So another question for the entire panel. Obviously, these are three very different types of technologies that we're talking about. And in the last panel, we kind of ended on standardization, data standardization being a really important factor to consider. And I guess as we think across different types of technologies, is that something that we have to think about? Are there standards in place for some of the data that you're collecting? Are there standardized outputs that you have to think about? And then wrapping in someone else's question, how do we start getting BOEM and other federal agencies to accept some of the specifications or to provide needed specifications that you can achieve? We can start down there.
Okay, I'll go first because this is like way out of my swim lane. But my understanding of some of the biggest challenges right now from a data perspective is quality. So, I mean, it makes no sense for me to go out, conduct a 7-day survey without being confident that the data that is captured and stored is usable. So how do we develop a system, a software apparatus that as data is populated, it can quality check it in real time and identify flaws as they arise? So first, is the data you collect high quality, and is there a system that can receive it and understand whether or not it is quality. And we have to define what that is, by the way. And then the second element of that is doing this at scale. As these solutions become more available and more popular, I think the amount of data produced is going to skyrocket. So making sure that whatever platform and whatever system is built can receive that in a responsible way will be really important. So yeah, that's my 2 cents.
So yeah, that's a very good point. Another thing I'm thinking about is more about how long you need to keep your data array. So it's different from the medical world. There's a regulation to tell you, hey, 6 years, you must have the data. It's traceable. But for these offshore assets, who will have that saying? Is it an insurance company or is it someone, the one from owner? So I think that needs to be figured out.
I'm going to give a slightly engineering answer because I'm an engineer. At a very low level, there are well understood data formats in most domains that we know how to process, how to distribute, deliver, process at scale. So when you get to imagery formats, when you get to bathymetric data formats, when you get to audio signal, acoustic signal data, there are underlying, the FLAC formats and the PNG formats and the like. Some sensing layers that are more mature, like bathymetry, do have structures and organizations in place, like International Hydrography Organization, that have attempted to specify some aspects of data quality that you can measure yourself and your sensing equipment to. Third-party sensors, like Kongsberg, Norbit, are well-versed operating in that domain. They produce fairly standardized data outputs that the downstream ecosystem knows how to consume. Other sensors, like imagery sensors, are a good example where while we have a data format, what data quality means can become very highly use case dependent, and that's a little harder to do. Just a broad domain, whether you're looking for fractures on turbines, whether you're looking for ice shelf characteristics, or doing a domain awareness, you're looking for ships. Use case can vary. Some cases it's, in the one that we're talking about, this week, marine mammal mitigation, it is very unformed. It's really even hard to point to something that says, what is the metric I even use to know if my detection is good enough? We have standards that literally are based on people with binoculars, and I would hesitate to even call it a metric. I don't know how to measure a solution to that. So that's really hard, and it's an area where the community can help drive standards. Without that kind of standards, it can be hard to drive commercial adoption. And we all want those standards to exist because it makes it much easier for us to build solutions, to build products to them. Otherwise, we're going out there and trying to convince every individual customer, person, and agency one at a time. That's not remotely scalable. And so I think it's a very mixed bag. It's often not lower level technical standards. It starts to get to business standards and regulatory standards that we need work.
Thanks, that was great. And I would say for more information on kind of that conversation, the Regional Wildlife Science Collaborative for Offshore Wind is starting to work with the Department of Energy and the Marine Technology Society and bringing together a bunch of different technology working groups to start having some of those discussions. Which is great. I've got a couple of specific questions for some of the projects. For the GE2 camera technology, up to what sea states do you expect to be able to collect data in? Specifically, they're asking about wave heights.
So currently, for the vessel itself, they can deal with as high as above 2 meters wave height. But for our imaging system, as I mentioned, is a proof of concept. We didn't focus on the water protection piece. We focus on the inspecting when turbines are operating and also the image quality. So if we get a chance to work on the next phase, water protection will be the focus. In that case, we want to have a comparable capability as the vessel. So we can, for the current test in the Block Island, the day we went there, September 2nd of this year, the wave height is about 1 meter.
Just to follow up on that question, someone was wondering, when you're looking at images of the blades, what is the kind of threshold for structural failure that you're looking for?
Yeah. it depends on which kind of defects we're looking at. So normally you're looking at leading edge erosion, you're looking at cracks, maybe some burnouts due to lightning, and some other denomination and so on and so forth. Maybe the visual camera cannot detect that. So it really depends on the defect type. That's one. Secondly, I think it's more from the OM repair practice perspective. How do you define your severity level? So in the industry, we use the category 1, 2, 3, 4, 5 to define the severity level. Each of these level indicates your repair actions. There's no single number to say, hey, above that number is catastrophic. Below that number is safe. It's really about economic calculation. Which level you want to take care of your action. So you can extend the life of your assets. You can make sure the structure health. So it's a complicated problem. There's no single answer to that question.
Thanks. Mary, we had a couple questions around the Dive LD system. One of them is, does the system possess a dynamic positioning system? In case not, is it planned for future developments for the vehicle?
Short answer, yes. The control system is something, it's fairly, I don't want to say rudimentary, but it operates in 3 planes. I mean, short answer, yes. I don't know how much further I need to get into that.
Maybe someone can come talk to you later this evening for more information on that.
More technical stuff, let's go offline. Thanks.
Okay. One more, maybe a little bit technical question, but around visual inspection for different types of mooring systems, so not just fixed foundation, but thinking about maybe floating technology as well?
Yes. I mean, when you say like applications of this technology to floating wind, okay. So that's actually where we're most excited. Turns out that going deep is more necessary off the coast of California and where floating wind will be required. So that's where I think we'll truly be able to shine. So this is absolutely something that we're looking to develop towards, and that involves not only for the moorings themselves, so you can do lines and waypoints that follow where the different foundations and where they're affixed, or the anchors are affixed to the floor, if at all, or following the cables as they are routed back to shore in the floating space. So long story short, we think that there's a lot of different ways that we could apply this technology to floating wind. It's just a matter of, again, I hate bringing it back to a chicken or the egg problem, allowing that market to take shape. And so just making sure that the way that we scale it is responsible.
Thanks. And a couple questions for Brian. Can you talk a little bit more about the detection ranges that you are seeing during your testing and how they're compared to maybe traditional omnidirectional hydrophones? And following up on that, for a lot of marine mammals, they are some species are more talkative than others, and how do you kind of account for being able to detect some, but not all marine mammals that are present?
Sure. First, this is part of the collaboration that we're doing with now RDC and RPS, is to understand these kind of characteristics. We haven't published range data on the current sensor. We're working to characterize that. In general, we have a variety of, the drones can carry a wide variety of sensors that, some of them can see many kilometers out, whether it is visual imagery and radar and the like. We'll have some sense, in the coming months where that particular passive acoustic array performs. And you're right, it does vary. We're seeing species variant. This is where we're listening to the scientists and learning here. In that some are very talkative and some are very quiet, and some have variant behavior. They talk sometimes, but not others. We believe part of the solution will be sort of a sensor fusion approach that says when you have thermal sensors, and our big camera has thermal sensing on it, when you can do thermal sensing and visual sensing and look for things like plumes and breaching in combination with acoustic sensing, passive acoustic sensing, you'll get a better read on a wider variety of them with a little, higher durability. Some of those sensors will work better in different conditions. Sea state variance is one of them. And so radar behaves differently when sea state gets high. We have a lot of experience of this. We send drones into hurricanes. If you haven't seen this, there's like a NOAA mission with sail drones and hurricanes. We've got a lot of experience about how cameras and sensors behave in sea states and wind and rain. And sometimes it's not even the radar, it's waves, but like visual sensing, when storms come in and there's a lot of rain, it's just literally hard to see through the air. Different, thermal sensing systems behave better. So we'll, as we get through the projects with Now RDC, get a sense of what is our ability to detect marine mammals at what range. In the end, though, the solve for that is our sensors will be at least as good, or what you can see on those buoy systems, and they will be mobile and they can work in concert. So we're capable of carrying the same kind of sensors. Our bigger boats can carry really anything those larger research vessels do too. So we're confident that our mobility combined with the sensor fusion should give at least or better the same net capability.
I feel like that also suggests the multiple method use. You can't necessarily see everything with one type of technology, and you might have to have a couple of different types of things out there to detect what you're looking for. And it's good to make sure that those things are working together. I have a couple more questions actually about the camera technology. And let's see. One, on how difficult is it to be able to detect something so small with the cameras in that environment? And then also, is there any difference in the effectiveness or limitations of using a marine drone versus an aerial drone in that environment?
So for the resolution itself, with a careful selection of the camera and the lens, we don't see the challenge here, and particularly because there's no strict limit in terms of your standard for distance. So as I mentioned, it could be from anywhere between 75 to 150 meters. You can get closer as well, but just make sure there's a safety distance between the vessel and the wind turbine towers. So that's not a challenge. What's your second question?
It was around the effectiveness of aerial versus marine drones.
Yeah, so you can define different metrics depending on what is your KPI. Without knowing the matrix, I cannot say which one is better or not. But I mentioned a few advantages in my presentation. Firstly, you can have a much more often inspection, which provide you more data, more confidence in terms of knowing what's going on, right? So for drone inspection, without knowing the condition, you may prescribe every 6 months or every 1 year to do the inspection. I mean, if you guys like me, a little bit from the AI perspective, so without frequent inspection, it's hard to really apply some machine learning AI method to help you build a prediction model. So from that perspective, I'm a big fan of doing the much frequent data connection with lower cost and a much safer way.
Thanks. And I think this question was directed at Brian and Saildrone, but potentially we can expand it for everyone. A lot of these systems are capable of doing many things at once. The question directed to you was if there are challenges including LiDAR on the Saildrone, but maybe just generally, how are you determining what types of data you're collecting, and how difficult is it if someone is like, well, can you also just throw in this measurement as well?
We do that a lot. You're a company, so you try to figure out you do some sensor development work because you think that use case in that market needs it and it's high value. So like LiDAR, upward-facing LiDAR for wind farm management's one of them, imagery, radar, et cetera. We built a platform and that is intended to be flexible and carry a wide variety of payloads, and so we've invested time and design into how do you mount them, power them, and get data to them, to and from them in a way that's relatively low touch so that we can flex the sensor payload. You go look at a market and you figure out just what are the key sensors. Sometimes like this experiment with Now RDC, it requires some experimentation to figure out if it is the right sensor. It sounds like a great idea and you got to go build it, test it, iterate it. And then you maybe realize that it is or it isn't, or it requires fusion. You kind of, with other sensors, and you have to work through that. Having, a fleet of drones, flexible drones, and that, we can go out and change out the payloads and do those experiments. We're pretty heavily customer driven today. You come to us with a use case, we work with you to figure out the right sensor set. And, in that it makes business sense, we can get different sensors on there.
Do this one. So we're probably a bad example of that. I don't know if you recall the image I showed you of all of the sensors that we somehow crammed into the Dive LD, but we have a lot of them. So again, some of this has been shaped by the market itself, but I do think that over time, certain sensors will be more frequently used, and then re-inspections and augmentation inspections can occur to add more detail to that larger picture. So, for example, the last slide I showed you, side scan, really popular, but even more compelling when you overlay it with magnetometer visuals. So that it adds to the bigger picture, but I agree with Brian. It is customer-driven, it is market-driven. We fit everything that we could into the Dive LD that we thought was pragmatic, but I do think that over the next couple of years, as these inspections become more frequent and we learn what is actually helpful and what is usable information, it'll dictate what gets more of the juice from the battery.
So maybe I just add on that. For above water assets, don't forget about the onshore, because onshore has such a long history and a best practice. So for us, for offshore applications, it's really about utilizing different vehicle, different platform to conduct the inspection data connection. So we basically leverage the onshore best practice in terms of what sensor to use, which defects to match which kind of a solution.
Okay, I think I have time for one last question for the group. One of the things that we've talked about has been maybe removing humans from some of the unsafe conditions that are out there, but are there opportunities that we should be thinking about that is going to be putting people to work in these applications? I'm kind of thinking, we're maybe not having them do the data collection, but there's a whole world of analysis that is popping up because of all the data that's being collected.
Thank you. That's so kind of you. I feel like we're going to have very similar answers. So it's not only the data side, but just because this vessel is autonomous doesn't mean it doesn't need babysitters, right? So I think there's going to be a lot of different field teams that are needed to go out and deploy, for lack of better words, with some of our autonomous vehicles to make sure that, one, it's working as expected mechanically, electronically, and software-wise, and two, it's actually collecting usable information and feeding that to data analysis teams and people that interact with the developers. So again, we're starting pretty slow, but I do think over time it's going to be a very field-heavy job as well.
Yeah, I definitely think if anything, it creates a lot of employment around it. Doing science, doing data analysis just enables so much more work to be done because we can cover so much more scale. But a couple of our customers have told us frequently, we don't have enough boats to do a fraction of all the work that we want. So no matter, I think, anytime soon how successful we are with autonomous sensing platforms, all of the existing resource crews and boats and people are still going to be out there doing a lot, and the autonomous systems just act as a force multiplier to the existing resources that are out there trying to solve these problems. We all want to get a lot more done. We all want to cover the oceans of the world with all of our sensing and thinking and monitoring and coexistence work, and I think the scale we get from autonomy is probably the only way we can do that.
I agree with what this said. Yeah. So the full automation is still a long-term vision. For short-term, totally human will be assisted. Human will be amplified with better safety and efficiency.
Thanks, everyone. And thank you to our panelists. I really appreciate all the presentations and the discussion with you. I think we have one more slide. Maybe we don't have a slide on this, but following this, I think we're reconvening back in the Pfizer auditorium for one last keynote talk tonight, and then you can meet all of our presenters later at the reception. So thank you very much.
And come and see some drones if you touch them. Selfies.